My name is Diego Fernandez. I'm the head of the Research and Development section here in ESRIN in the Directorate of Earth Observation Programs. And I would like to welcome you to ESA, welcome you to ESRIN, and welcome you to the summer school 2018. So I will give you just an introduction to the activities of the Space Agency, of the European Space Agency. I don't know how familiar you are with it. And I will try to give you also a panorama for missions and give you some examples of the capability that satellites have for science as an introduction to the different lectures that you will have during all these 2 weeks. So let's start by ESRIN. You are in the Italian Center of the European Space Agency. We like to call it the Earth Observation Center of ESA, even if our colleagues in ESTEC will be very unhappy because actually they design the satellites and they test the satellites up there in Norwich. But here, from here, we manage, I think, the most sophisticated ground segment of Earth observation in the world. We have also the team that is exploiting all the missions, but we are trying to maximize the impact of those missions in terms of science, in terms of applications, in terms of services for the citizens. And on top of that, we have other services here. We have the team that is building the Vega launcher, and we have also all the informatics group of the agency. ESA, for those that doesn't know what it is a international convention. It's actually a treaty. It's an intergovernmental organization with 22 member states, and this is actually the purpose of the agency, which is written in the Article 2 of this treaty. And in practical terms, it says that we are here to provide for and promote for peaceful purposes cooperation among our member states in space research, technology, and their applications. To understand exactly what it means, if you go to the dictionary and you look for provide for, you find 4 meanings. And I think those 4 meanings explain very well what ESA is. The first meaning is allow. We allow all these things to happen. We allow the cooperation between member states. The other meaning is to take care. So we take care of a space. It's something very close to our hearts. The other meaning is to make things happening in the future. And this is also very important because this is a scientific research and technology organization, so our main purpose is to prepare the future of the space technology and how to be used for citizens. And the final one, and this when everybody starts to smile when I make these presentations, is to pay for. Practical terms, our member states finance our programs, and we implement those programs through contracts with scientists, with industry, with institutions all around Europe. This is how ESA is distributed all around the world. We have several centers in Europe. The biggest center is in Norwich, it's our technology center. We have our headquarters in Paris. We have our flight operations center in Darmstadt. We have offices all around the world, and we have a launcher site in Kourou, in Guyana. We are one of the few space sciences in the world that takes care of most of the areas in space research and technology. We build launches, we have astronauts, we take care of planetary exploration, we take care of extraplanetary science, we take care of Earth observation, navigation, all types of different activities in space. And I would like to show you first, before coming to Earth observation, some results of all these activities, because ESA is not only Earth observation. Probably you recall all this, okay? This is a comet, actually, where Europe has landed. So this is the Rosetta mission. It has been flying for 10 years. And after 10 years, we have been able to launch a small robot and a small lander and to put it there to take measurements of the comet. It was a very tricky operation because after all these years flying, the lander was supposed to have a propulsion system that was not working to separate from the main spacecraft. So that was not working. And actually, it was supposed to have a system to attach the lander to the comet, and it didn't work. So in practical terms, the guys operating the satellite or the spacecraft just drop the lander and leave the lander fall down thanks to gravity. It bounced over the comet, and at the end it arrived to there and landed in this side. You have a photo actually of Philae over the comet. And this is a photo taken by Philae. So I think no one has been so close to a comet ever. Maybe a dinosaur, but had not an opportunity to take a picture. The interesting thing of this is not only that you arrive to the comet, it's all the science that you can do with the measurements that you are taking. So they have discovered interesting things, like for instance, the composition of the water in the comet is exactly not the same as the composition of the water on the Earth. And this is very interesting because one of the theories around is that the water in our planet came from comets. Well, this leaves still the question open. They have discovered also oxygen around the comet. Not the oxygen that is coming maybe from other sources, from the water vapor, etc., but other type of oxygen. They have discovered also nitrogen. So all these parts of what is life in our solar system. Probably you also recognize this, and Europe has been also the first one to land on a moon of Saturn. And this is Huygens that has been launched also over Titan. Titan is a fantastic world made of methane, liquid methane. So it has a cycle of the water cycle on the Earth, but done by methane. And this is the pictures that Huygens has been taken while falling down through the atmosphere of Titan, and took that fantastic picture there when arrived to the land. This is a fantastic photograph of Mars, taken by Mars Express. And this is a storm, a sandstorm in Mars. So we are able to get pictures like this of our neighboring planet. I like also this one very much because this is a big crater, and the thing that you see there is a cascade of sand in a huge crater on Mars. And now let's talk about a little bit, let's get far away in time and in space from our solar system and think about the origins of the universe. We have a mission that is called Planck that was trying to make a picture of the baby universe. At the beginning of the Big Bang, after a few milliseconds, the universe has been expanded, and all the matter and energy has been mixed for a while. So with the first particles have been created, mainly protons, electrons, neutrinos. The photons created when these particles were bouncing had not the space to travel because the universe was so dense that always was finding, these photons were always finding other particles in the middle, so they could not travel. But at a certain point in time, the universe just expanded enough to leave those photons to travel in space. And this is the image that Planck took. So this is a picture of the universe after 300,000 years from the Big Bang. It's what is called the cosmic microwave background. You can see the structures there, hot structures, or more dense structures in red, more cold structures in blue, and all the stars, all the galaxies has been created around these hot spots. But more than that, Planck was able also to map the polarization of that energy with incredible level of resolution. You will recognize this. This is called the pillars of the universe. It's a very nice photo taken by Hubble. And Hubble, everybody believes it's a NASA mission. Well, it's a ESA NASA mission. ESA has contributed significantly to Hubble, to the electronics of the satellite, allowing to take all these fantastic pictures. This is very nice. It's very famous. Probably you know it. Scientists decided to point Hubble towards, well, they believe it was an empty piece of space during 10 days, collecting all the light arriving to the telescope. And they discovered this, more than 10,000 galaxies in a place where they supposed it was nothing. Amazing. Well, now we are going to talk about this. This is also Earth observation from distance. This is a picture taken by the Voyager. And this dot is our planet, is where we live, is what everything happens. And to observe that planet as another planet in the solar system, we use satellites. And this is what we call the ESA fleet. Actually, it's not only the ESA fleet. This is the result of a fantastic effort in Europe that involves many institutions and many people. It involves the European Commission, involves EUMETSAT, involves industry, involves scientists. Our fleet is organized around 3 main pillars. We have the meteorological missions that started in the 70s with the launch of the Meteosat. And every time that you look at the weather forecast, all the images coming to do that came from this type of missions. Copernicus is another pillar. It's a fantastic endeavor in collaboration with the European Commission to develop an operational infrastructure in space to serve European policies. And the last pillar is our science pillar and includes a series of satellites that are called the Earth Explorers. The Earth Explorers are really a very strange combination between 2 main aspects. The first one is technology. All of them are really masterpieces of technology. They have to push technology to the limits, while at the same time, this is the second component, they have to address a very specific objective, a very challenging open question in science. I was hesitating to show you this animation now in the beginning or at the end, but I think that it's very important that you see it now because later on that puts everything in context. You will see many missions, you will see what those missions can do, but the most interesting thing for you, the most interesting thing for us in the coming decade is the synergic capacity of all those missions. It's how to use all the different type of information and how to exploit the complementarity of all those missions in a synergistic manner to study the Earth system. This animation we have created to promote a tool that we have developed, which is called the Earth System Data Lab. And the Earth System Data Lab contains more than 30 different variables that characterize the different components of the Earth system, mainly focused on land, but also focused on the ocean. And attached to that, we have a number of functions of code to help you to explore that hypercube of data. And during these 2 weeks, you will have an opportunity to play with this. So let's go a little bit to see the missions that we have. This is a panorama of our Sentinels. We have right now 7 flying. And let's go with Sentinel-1. Sentinel-1 is a radar mission. It's a synthetic aperture radar in C-band. It's very useful for many things, for several applications, to map sea ice, to look at flats, to look at ships, to also to do very strange things like study earthquakes and volcanoes. Has been instrumental also in cryosphere research. It allows to measure movements on land. It allows to measure the velocity of the glaciers in Greenland and Antarctica. And that has been, in science, one of the main contributors to understand how Greenland and Antarctica are contributing to sea level rise. It also have, using a technique that is called permanent scatters, it allows you to monitor land subsidence, or how the land is moving at millimeter level. And this is a nice example over San Francisco. Let's focus here. And there you can see in the color bars how things are moving. And we have detected a hot spot in the Millennium Tower. The Millennium Tower is actually sinking a few millimeters per year, so probably after a couple of million years you will be able to get into the building through the 2nd floor. And that has had a incredible repercussion obviously in all international media. I would like to show you also this, which is also, I told you before that interferometer is a very useful technique to measure the velocity of glaciers. But it's also a very useful technique to measure the movement of the ice shelves, which is the floating part of the glaciers, because of the tides of the ocean. So using interferometry, the thing that you can do is to understand this movement and to delineate what is called the grounding line. And the grounding line is a very important parameter because actually it gives us information about how the glacier is evolving, is retreating or is advancing. And this is an important component to understand the climate system there. And actually, it's also an important component to compute how much mass is leaving this glacier. I would like to show you also this example of how interferometry can be used. I told you before that it's useful for volcanoes and earthquakes. And I think this is a very nice example. These are real faults, and these are real earthquakes that happened during that period. Everything that you are looking in these animations is not fake, it's real data. Okay? So this is a study that we have done together with the University of Bristol to understand the behavior of the African rift. And to do that, we use a lot of different data during several years to map the volcanoes' evolution, how they are moving. So using interferometry, the thing that you can do is to see how these volcanoes have been growing and breathing in time. So each one of these interferometry lines show you different displacements in the volcanoes. But maybe more interesting is what we have done with an earthquake that happened in this area. And in particular time, the interferograms also show you how the land has been moving. We have several earthquakes in this area in 2009. And the earthquakes have created a different, certain pattern in the interferogram. So using different SAR imagers, in particular Salos pulsar in this case, we have produced an interferogram. And the interferogram was telling us that actually to have this type of interferogram, you need a fault that was not there before. That means that we have discovered a new fault thanks to interferometry that was not before mapped. I think it's a remarkable example of how Earth observation can also help us to understand the solid Earth. Over the ocean, we can do very nice things with SAR like this. This is what we call firewalls. These are swells. These are waves that are created by storms, and they are propagating all around the ocean. So that energy is propagated all around the oceans. We are able to map those with SAR data. Sentinel-2 is our land mission. It's built upon the heritage of SPOT. It's built upon the heritage of Landsat. And it's mainly a mission dedicated to map the land. It's maybe a mission dedicated to agriculture, to understanding changes on our landscape at high resolution. But it's also a mission that is collected over coastal areas all around the world. And I would like to show you this, because this shows you very nice the potential that also this mission have for oceanography. And if you have oceanographers here, they will recognize two things. This is a fantastic algal bloom, actually it's in the Baltic, but at the same time, in terms of physical oceanography, this is a super well-resolved eddy. So there is information there about the biology, and there is information there about the physics of the ocean. Sentinel-3 is actually our ocean mission. It has 4 different sensors. It has an ocean color sensor, has a thermal radiometer, has the first operational SAR altimeter, have a passive microwave radiometer. And the interesting thing of this mission is actually what I told you before, is the combination of all those measurements that allows you to make science addressing different components of the Earth system. I would like to show you this example. It came from a project that is called Ocean Flux. We did that in collaboration with SOLAS, which is an international group, an international program dedicated to study ocean-atmosphere interactions. So imagine that you want to measure the ocean fluxes, the CO2 ocean fluxes. You will need different type of information. You will need the temperature of the oceans. You will need information about the roughness. You will need information about the waves. You will need information about anything that may impact solubility, maybe salinity, temperature, etc. But also how the CO2 may be transferred from the ocean to the atmosphere and vice versa. So that means the effect of the wind over the surface of the ocean. So the thing that we have done is we have collected all that information, and we have created different layers of information. And we have also did a lot of research to improve the parameterizations, to improve the gas transfer velocity, and at the end we compute a new climatology of CO2 fluxes. But the most interesting thing for you also is that we have put all that together in internet. So you have a tool right now which is called Ocean Flux Engine. And if you go to the web, you will find all these different layers available to you. You can choose from the different parameterizations that has been published by scientists, and you can compute your own climatology as you prefer. So we put together information about rainfall, significant wave height, wind speeds, ocean color, sea surface temperature, etc. And then we have merged all that together with in situ data. In particular, we use data from the SOCAT project that is collecting PCO2, which is the pressure of CO2, in practical terms, a proxy from the concentration of CO2 in the ocean. And this is the result. This is, I think, the first climatology of CO2 fluxes based on Earth observation data. You can do that. You can compute your own climatology and to publish it with your own new paper. Looking at the atmosphere, I would like to talk to you just briefly about Sentinel FP. It has been launched very recently, and it provides it's kind of a revolution in atmospheric chemistry, because it's actually providing information about different species in the atmosphere with incredible amount of detail and a resolution that was impossible before. So these are some of the first results. They have been published in EU this year, like CanMI and DLR, and it includes several species. This is just an example of NO2, SO2, methane emissions, aerosols, etc. I think this could be really an instrumental mission in order to better understand the carbon cycle, to better understand the impacts of the carbon cycle in the climate system, especially taking into account the methane emissions. This is just a picture coming from Skemaki. Skemaki was another sensor, a precursor of this that was flying on ENVISAT. And this shows the evolution of methane until 2010. The interesting thing is that after 2010, something happened in the methane emissions, and nobody knows why. This curve that you can see at the end started to continue growing, and it's unclear where all these emissions come from. So Sentinel FP will be actually instrumental to discover where those emissions come from. All this data is freely available. All this data is just there. You can download it. You can download it from the ESA Science Hub. You can get it from Amazon. You can use it in Google Engine. It's everywhere. It's free. Okay? So this is a thing that actually we hope will really accelerate, let's say, science and the development of new applications. To facilitate this process, we are developing tools for scientists. You will have an opportunity to play during these 2 weeks with those tools. One is a Snap. I think this afternoon you will start playing with it. But we're also developing something that is called virtual labs. And virtual labs are environments where scientists access through internet data, Earth observation data, high-level products produced by different data providers, and actually you have the opportunity to process all these data online together with in situ data. You will have also an opportunity to play with this nice tool, which is called the Ocean Data Lab, during these 2 weeks. We are thinking now about the future of the Sentinels. We are preparing a number of studies to explore the potential evolution of the Sentinels. And we are looking to these candidate missions, an anthropogenic CO2 monitoring mission, a high-resolution thermal infrared mission. We are looking also at passive microwave, like high resolution for oceans and ice. We are looking also on a spectral imaging mission, and finally we're trying to further expand the series of C-band radars with an L-band radar mission. And now let's talk a little bit about explorers. As I told you before, these missions are a nice combination of technology and science. I will show you some examples. Gotcha is not flying anymore, but I think it was a real success. This mission was supposed to map the geoid. It has a very precise objective. During 3 years, was taking measurements of the gravity field, in particular the gravity gradients, which is the variation of the gravity field in space, to map that, which is a geoid, which is in practical terms the theoretical surface of all the masses of the Earth and their stability. And this is very important for geodesy, very important for oceanography, because it represents a reference surface, for instance, to compute things like this, which are the ocean currents, the geostrophic currents. But Gotcha has been also instrumental to do many other things that we have not thought when we have created it. Gotcha had a system, was flying very low in order to get a good signal of the gravity. And to maintain that altitude was around 200 and few kilometers. To maintain that altitude, it has a system, was a thruster system, to compensate for the resistance of the satellite with the atmosphere. Still at that altitude, you are in the middle of the thermosphere, so you have a lot of air particles actually that are making resistance in the flight of the satellite. So we use that information actually to measure the density of the thermosphere. And that data set is very important because it allows to model better the thermosphere and can be very useful to estimate better how satellites will behave at those altitudes. But as a curiosity, also during the flight of Gotcha, you probably remember we have the Tohoku earthquake in March 2011. That earthquake created a wave, actually. The Earth is moving, a big shock, and this is transferred to the atmosphere. That energy is transferred to the atmosphere as a wave of infrasounds. And this is propagating in the atmosphere. And when it arrived to the altitude of Gotcha, actually, as we were measuring this density, actually the satellite just bounced because of the sound wave that arrived from the earthquake. And this is real data, actually. It was actually like this. So we call it the first seismometer in space. Gotcha was also instrumental also to improve our understanding of the solid Earth. In practical terms, the gravity information that Gotcha is collecting through an instrument that is measuring the gravity variations, the gravity field variations in all directions. And this gives us information about the distribution of the different masses in the lithosphere. So the gradients of the mass distribution. This has been used, for instance, to measure the crust height, so how deep is our crust. This is called the moho. And this is the difference between the previous existing map and the map of the crust thickness provided by Gotcha. This is the first time that has been done globally at this level of resolution and detail. But we went further, and we were trying to explore also that scientific results into an application context. And one of these application contexts is the oil exploration. We wanted to understand if it's possible, for instance, as in this case, to use this data to explore or to understand the maturity of the hydrocarbons present in the lithosphere. To do that, you need a good lithospheric model, and this was done thanks to Gotcha. And through that model, you can compute the temperature, you can compute the pressure, and then with that, you can understand if the hydrocarbons present in that area are mature enough to be explored. Cryosat is our ice mission. It has been mainly dedicated to measure sea ice thickness in the Arctic. It has been also instrumental to measure, obviously, the elevation and the elevation changes in the ice sheets in Greenland and Antarctica. Has been providing a fantastic contribution to the understanding of the contributions of those parts of the planet to the sea level. This is an example of the cumulative volume of sea ice, of ice loss over Greenland. And actually, we will move now to the Arctic sea ice to show how it evolves. These measurements are taken thanks to the altimetry capabilities of Cryosat, which actually, for the first time, use a technique that is called SAR altimetry, that now is operational on board of Sentinel 3. So it has been a precursor, actually, for the latest generations of altimeters. This is how the sea ice volume evolves. The volume is derived from the sea ice thickness. And actually, Cryosat is measuring what is called the freeboard. So it's measuring how this distance between the water and the top of the ice. But Cryosat is an altimeter, and as all altimeters provide information also about the oceans. And this is an example of the mean dynamic topography over the oceans. And also provides information about the currents. And these are a very nice picture also of how the currents, the dynamic ocean topography has been derived from Cryosat. There is something that I like a lot, which is unique of Cryosat. Cryosat has two antennas. That means that it can collect the echoes from the ground in two different directions. And this allows to resolve let's hope it's working. Yes. It allows to resolve the altimeter echoes not only along track, but also across track. And that means that you can pass from something like this, which is what a traditional altimeter can give you, to a complete image of the elevations. This is an example of an ice shelf. And the interesting thing of this, as I told you before, is the synergy with other data. So using information about the velocity of the glacier, using information coming from models on the snow accumulation, we were able to map the basal melting of the ice shelf. The first thing that we have discovered is that there is a channel in this ice shelf, and this channel is increasing. And this is created by the currents in that area. The currents is accelerating the melting across this big channel in the ice shelf. And you can see here the changes in elevation, and this red area there is a big channel that is increasing in time. So the estimates are that in 50 years, if the melting rate continues, the ice shelf will collapse. So a very nice discovery also from Cryosat in combination with other data. SMOS is our ocean salinity and surface soil moisture mission, but also has been very prolific. You have to understand that this was the first L-band radiometer, synthetic radiometer in space. And when scientists have the opportunity to have a new toy in space, they try to do all types of weird things with it. So the thing that we have tried to do, for instance, is to use the information of SMOS to measure winds, and in particular very strong winds, in particular the winds provided by hurricanes. And this is what we have done actually. It works very well, and is even overcoming some of the limitations of current missions that saturates to a certain level at 35 meters per second. It saturates. So SMOS doesn't saturate, which provides new information for scientists and forecasters. Interesting enough, combining the salinity of SMOS and combining the winds of SMOS, we could also try to reveal why the hurricanes that are crossing the Amazonas plume are not losing energy and momentum. In practical terms, all the hurricanes by statistics that are crossing the Amazonas plume are always of high category, category 5, category 6. This is because actually the salinity, the low salinity layer created by the river is actually hindering or is avoiding this exchange of energy between the ocean and the hurricane, and then it's not losing energy. And we have seen here that it was crossing, it was just moving away an enormous quantity of fresh water as big as UK. It has been also useful to map sea ice thickness. And this is a very nice thing because actually Cryosat can only provide ice thickness. It's looking for the freeboard, can provide ice thickness over 0.5 meters. But with a SMOS, you can retrieve between 0 and 0.5. So the combination of these two are a fantastic opportunity to study sea ice thickness evolution in the Arctic and Antarctica. So I arrive into the end, just a few more slides. This is SWARM. We will have an opportunity also during these 2 weeks. I think the last 2 days will be mainly dedicated also to SWARM. And it's looking at the magnetic field of the Earth, which is actually this one. It's looking at the ionospheric physics, ionospheric dynamics. It's a very interesting mission. And we are close to launch EOLUS. EOLUS will be launched in August. The 21st of August it will be launched. And this will be the first time that we will be able to provide profiles, 3D profiles of winds in the atmosphere. So be ready for the launch of this. And we're preparing other satellites. We're preparing EarthCare that is trying to explore the interactions between clouds, between the aerosols, in terms to understand better this component of the radiation budget of the Earth. And we're preparing biomass, which is a PVANSAR that is trying to measure biomass in our planet, mainly from the tropical forest. We are developing also FLEX, which is looking at the photosynthetic activity of plants. So the combination of these two missions will be really fantastic to really understand better the carbon cycle. We have right now 2 candidate missions. One is called Forum, that is trying to look at the far infrared part of the spectra of the emitting radiation. We have another mission, which is called SCHEME, that is trying to resolve for the first time at higher resolution ocean currents in all directions. And with this, I would like to close my talk. I would like really to thank you for the attention. And these 2 weeks, please don't be shy. You will have an opportunity to have here some of the top scientists in the world. This is an opportunity that is not very common. So take advantage of that, ask questions, interact with them. And that's it. I really wish you a fantastic time in Frascati. Thank you. Thank you.
This is the 9th ESA EO Summer School. As you see from the photo, this was the last summer school 2 years ago. This is something that takes place every 2 years. Also with you, in a few days, we'll do a nice group photo. This year we have 70 early career scientists. In fact, always the participants of the summer schools are considered early career scientists, so PhD postdoc level students. This year you're from 17 different countries. The topic of the summer school is Earth System Science, Monitoring and Modeling. This includes Earth System Modeling, so understanding the oceans, the land surfaces, the solid Earth, atmosphere, cryosphere, and how they interact with each other. Can you hear me okay? Yes. It also includes observing these different systems, not just with satellites, but also with in situ and other remote platforms. And then it includes data assimilation. So how do we assimilate this data into models to better understand the Earth system? This year we have 15 different lecturers, leading scientists, and we also have 13 trainers for the practical sessions in the afternoons. The program this year includes a week dedicated more or less to ocean cryosphere. The first day is on the Earth system as a whole. Then we have a day focusing on the water cycle, actually the water cycle over land. But then the last 3 days are focusing on the ocean and the cryosphere. In the afternoons, we have practical sessions. So first, talking about the toolboxes, the ESA Earth observation toolboxes. Then we will have some days dedicated to the Ocean Virtual Lab, so all about how to visualize and analyze different oceanic parameters. Today, at the end of the practical sessions, we'll have a cocktail reception. It's like an icebreaker, so you can get to know each other. Then on the fourth day, we'll have a dinner. Here we have most of the lecturers. Then on the second week, so here we see all the most of the providers of the practical sessions. On the second week, we'll start off with talking about the land surface, the carbon cycle, mainly the carbon cycle over land, in the land and in the atmosphere. Then in the afternoons, we have practical sessions on the Earth System Data Lab and also on data assimilation. On the last few days, we'll have some days dedicated to the ionosphere, the magnetosphere, and the solid Earth. So just some logistics. You are at the moment in what we call the Magellan room, which is this room over here. And this is where we'll have all the lectures. Okay, so in the mornings, you'll always be in this room. Then in the afternoons, you'll be in what we call the big hall, which is actually just up the road. If instead of, as you come up from the gate, instead of turning into this building, you go a little bit further until you see this totem, okay? And you go through that door, and then it leads into the big hall. So that's where we'll have the practical sessions in the afternoons. If you have any problems during the summer school, you can speak to one of us, okay? So I don't know if any of them are here right now in the room. In any case, Julia and Matteo are at the registration desk. And then Ula will be here, and you can always talk to me. You should have received, when you arrived, a PDF, okay? And this is a welcome document, including all kinds of logistical information. So you have information about the taxis, useful telephone numbers in case of emergencies. Also, you have the schedule of the shuttle bus that will take you from here to the Villa Tuscolana or to Frascati. You also have information about trains, okay, if you want to go to Rome from Frascati or from here, from the station of Tor Vergata, which is slightly different, different from the station of Frascati. Then there's also information about public transport in general. And then some other information. You should have received a rucksack on registration, okay? And at the end of the summer school, you'll receive a certificate of attendance. Okay, you can do with that whatever you wish. At the end of the summer school, you'll also be asked to complete a questionnaire. Okay, so we can see what your opinion was and find out how to improve the next summer school. And with that, I wish you a very nice summer school, and above all, a great stay in Frascati. And if there are any questions, then I don't know if anyone has any questions now. Yep. Are
we going to receive the lectures at the end of the summer school?
Yes, so all the lectures will be online at the end of the summer school. Or sometime after the end of the summer school, because we need to give the lecturers a chance to tidy up their presentations and give us a PDF version we can distribute. But also, all the lectures are streamed, so you can watch the videos of the lectures anytime. Okay. So if there are no other questions, then I'll introduce the first speaker, Dr. Annie Casanova, who will provide the first presentation of the summer school.